Okay. So we start, okay?
Yes, today, dear colleagues, today we have a lecture of Professor Verón, who is collaborating with us during many, many years. I mean, not only with our university, but also with many other Russian and Ukrainian universities. He was collaborating during many years with Professor Pakhajaev, with Professor Shishkov. So he's our old and true friend, and his results are internationally known. Therefore, it's great pleasure for us to listen to his lecture today. The title of his lecture is Initial Trace of Solutions of Semilinear Heat Equation. So we have approximately 1 hour plus discussion after seminar. Now, Professor Veron, please start.
Yes, okay, I start. So it's a great pleasure for me to be there, at least by screen. You know, the first time I went to Moscow, it was in 1974. It's a very long time ago.
Yes, really.
And I went from Moscow up to Irkutsk at that time.
Ah, interesting.
Oh yeah, so I visited a lot of things from Moscow, Irkutsk, Bratsk, and after that I went probably 10 times there. Okay, I would like to discuss of some results. I think they are. I think it's a work which started maybe more than 20 years ago, 25 years ago, and it has essentially now reached its maturity, and it's a question of notion of trace, boundary trace for solution. But this boundary trace today is going to be the initial trace for an equation of evolution, which the heat equation. And okay, my question is, okay, so this is not what I wanted. Yeah. So the question is, want to understand a little some precise asymptotics and behavior of solution of the semilinear heat equation. It's a very classical one, positive solution of the equation is dtu minus Laplacian of u plus u to the q is 0, where in Rn times 0 plus infinity, and in the superlinear case, because it's the one which is interesting, that means q is bigger than 1. So what we want to show that you take any positive solution of this equation, then I'm going to show that there exists a unique positive outer regular Borel measure mu on Rn, such that this that u of at 0 is equal to mu in the notion of extended trace sense. Outer regular Borel measure means that this measure can be plus infinity on points or any compact set. So it's not a Radon measure, okay? And we have a notion of criticality, which will be very important. And the notion after that will show that in the subcritical case, we have very precise estimates, which are obtained by using self-similar solution, which are the one discovered by Brésis, Terman, Pelletier 30 years ago. And which a tool, it's a kind of microscope to study this equation. When Q is supercritical, these estimates are much more complicated and they are going to be expressed in terms of capacitary potential of the measure. But I will insist more on the subcritical case because the proofs are much easily understandable. Okay, we start with very simple observation for the heat equation, positive solution of the heat equation 1,1. You take a solution which is C2 in a cylinder. Cylinder is Rn times 0, 0T. Okay, you take a positive solution, you take G to be a smooth and bounded domain in Rn. You call phi j the first normalized eigenfunction of minus Laplacian in the space W120 of G, and you multiply by phi j, and you integrate. So what you get the derivative d over dt of integral of u of xt. You multiply by phi square in order to have a plus phi square g plus twice the first eigenvalue lambda g integral over g of u xt phi g square. This is equal to integral over g of u xt phi square. It could be a 2 here. It's not missing, it's not important in any case. So the phi square, I have used the phi square in order to avoid the boundary normal derivative. Okay, but I have the price for that. This is introduction of this term here. Now I take the cylinder. In the cylinder 0t times g, the function t maps exponential of 2 lambda gt times integral of u xt phi square of g dx is increasing. So you have a positive function which is increasing. So it admits a finite limit when t goes to 0, which is a non-negative limit. Okay, it's a non-negative, so I call it mu of g. This is a limit just of this function, positive function. Okay. So if I integrate now my above equation between 0 and t, I have this one, exponential of 2 lambda gt integral of u x t phi j square minus the limit here is equal to integral on the cylinder of exponential 2 lambda gt u x t grad phi g square. Okay. Now, this is easy to see that this implies that for any, that the function u is in L1, because remember that before it has a limit, it's increasing and the function integral of u x t phi g square is increasing, and it has up the exponential term, but it plays no role, and it has a limit. So this implies that that u belongs to the L1 of the cylinder. Okay, and when you write this, you have d over dt of integral of g of u x t zeta plus integral from t to 1 to integral over g, it could be capital T, of u x s Laplacian of zeta. This is 0. Okay. This is just now multiplying by a test function. You take a test function and then you integrate like that. Okay. So what does it say? Here, remember that u is in L1 of the cylinder. Delta z is bounded. So this implies that this term here, when t goes to 0, admits a limit. So if it admits a limit, the derivative now, this implies that the function t maps integral over g of u x t zeta admit a finite limit when t goes to 0. Okay, since u is a positive, this limit is a positive functional acting on infinity of 0 function. So it is a measure. So it's a measure, it's a local measure, but after by a partition of unity, you have the full measure, which is the initial trace of heat equation, of positive solution of heat equation. This is something which is known for, I think that maybe 70 years or more, even more. And now the property of this trace of heat equation are well known. And when for positive solutions, there is no difficulty. There is I think the problem is completely known. The measure mu must satisfy this growth condition here. Integral of BR of exponential minus 1 over 40 exponential times x squared dmu of x finite. Okay, so this is, of course, this has not been in the case. Remember that the Petrovsky counterexample was for changing sign non-uniqueness for heat equation was for a solution with changing sign. Okay. So now with this, you have, of course, the Gaussian Gauss representation. So presentation of the equation of the solution. So this is the basic for heat equation. And now for the nonlinear equation. The nonlinear equation, the terms which plays a fundamental role, I take Qt or Q1, for example, and G is any open subset. Now, the question, everything will happen on what is the integral of UQ on the cylinder Q1. Either it is finite or not finite. Okay, this integral. Okay, now if this integral of integral of 0 to 1 of integral over G of UQ is finite, then essentially the terms UQ is just a perturbation, L1 perturbation of the heat equation. So there is no big surprise to see that in that case, there is again a random measure on G such that for all zeta in C infinity of compact support in G, you have the limit of integral over G of U x t zeta is integral of zeta d mu. Okay, this is the first case. The proof is exactly the same as in the linear case up to small perturbation. Now in okay, now you have actually a dichotomy. You have a dichotomy which is the following. Take U is a positive solution of ut minus delta U plus UQ. Okay, and you take any y in Rn, then you have the possibility, the following possibility. Either the integral, either there exists an open neighborhood gy of y, such that the integral on 0 to 1 of gy of uq dx dt is finite. So in that case, there exists a positive linear functional L on gy such that the limit when t goes to 0 of the integral of gy of u x t zeta dx is L of zeta for all functions zeta belonging to C infinity 0 of gy. So this is a case, the measure case, the simple case, okay? But this may not be always finite. And this is the problem of the dichotomy. You can have also this one, either or for any open neighborhood G of y, this integral is infinite, okay? And in that case, it implies that the limit when t goes to 0 of integral over G of u x t dx is infinite. This is very easy to obtain, and I'm going to show you briefly the idea. The idea is you take G to be bounded, phi G, again, the first eigenfunction of a minus Laplacian with zero boundary condition on G. And you multiply by phi J to the alpha with some alpha bigger than 2. And what you get? You get this identity. In this identity, you have two types of terms. Okay, you have this, the leading term is this one, of course. This is the important term. It is one important term. This one is nothing because we shall absorb this here, because remember, we're interested to what happened at t equals to 0. We will absorb by an exponential of t alpha lambda g. So it's not a problem. So we have this term here, which is the parasite term, and we have the term coming from the real nonlinearity terms. Essentially, what we are going to say, we are going to absorb this term by this one, thanks to Hölder inequality. So here you have integral of u phi j to the alpha minus 2 Laplacian of phi g square is bounded by integral of uq phi j to the alpha 1 over q times integral of integral over G of phi j to the alpha minus 2q prime grad phi j to the 2q prime to 1 over q prime. Remember that phi j is smooth, so not a problem. And now we take, in the particular case, so we are going to have by Hölder inequality, we have this, okay? And now you take alpha equal to q prime, and essentially the term, the parasite term, which was this one, has been absorbed by this one. So if this one is infinite, this plays no role, of course. This plays not role because it's in L1. So if this term is infinite, that means it will drive the behavior of the solution. So we write like this. Now we have this simple expression that you d over dt of exponential of alpha lambda dt integral of u phi alpha. Okay, this plays no real role. It's just for funny. And this plus this one is positive or 0. So this is an important term. So the consequence is that this here, this expression is decreasing respect to t. This expression is decreasing respect to t. And so the question, if of course, it can be negative, but it's not real problem. Now, if this term is finite, so this implies, of course, that this admits a finite limit because it's decreasing. The perturbation term is this one is the integral from 0 to 1 of this term is finite. So we have this. If it is finite, we have just say a smooth limit. Okay, but this corresponds to the case I. Now the second case is where this expression is infinite. So if this expression is infinite, we are going to make a small perturbation in order to have to absorb the gradient term, but we take the here. I want to take in Hölder inequality, I take a minus alpha term so that this term is dominant, and the result here is that this expression, this term here, d over dt of exponential of alpha lambda gt times this one, plus this expression minus this perturbation term, which plays not real role, is negative. But this one is infinite. This will play an important role, of course. And you write like this. Now the equation of the term here, it is just integration of some cylinder. It goes to some, it's bounded from times a constant times t minus c times 1 minus s. So you have this expression. And now when t goes to 0, okay, this goes to this term here goes to infinity. Okay, so minus here goes to minus infinity. So in order this to be negative, this one, of course, should go to infinity. Okay, now you have this dichotomy of terms. So you have this. This implies that you have this one term here. Okay. Now you see that you have a partition of points. You have the point y such that you have there exists this type of neighborhood in which the integral of uq in this neighborhood is finite. To this type of point, locally, there exists a measure. And now you, by partition of unity, you have construct the measure of all this set of points. This set of points here, the regular set is open. Is open because you take for any point you have a neighborhood of it. So you have a.
Sorry, Laurent.
Yeah.
I would like to ask you, what does it mean? C infinity sub C. This is set of infinitely differentiable and what?
And compact support. And compact support. Yeah, sometimes people.
We denote such set as C infinity 0.
No, yes. Okay, this is the same. It depends on the notation you have.
Okay, I understand. I guess.
Okay, this is a this is a space of test function.
I understand. Thank you.
So you have now the set of regular points is a set that your integral of a cylinder, locally integral of a cylinder of UQ is finite. It's an open set, and on this set there exists a radon measure. Okay. Now you have the complement, which is the singular set, which is a complement on the regular set. On the singular set, well, we know that if you take any point in the singular set is closed. You take any point in the singular set, you take any ball around this point, then the integral of u on this ball tends to infinity when t goes to 0. So this is a dichotomy of this. This is just made by the fact that this integral of uq is finite or not locally. No, yeah, so this is an important fact that if you have a point y in the singular set, then for any open neighborhood G of y, you have the limit of integral of uxt over G is infinite. So you have this couple S mu is first, it is uniquely defined. It's called the initial trace of U, which is represented by you have a radon part and the part where the solution blows up in this sense. You can associate to this initial trace an autoregular Borel merger that you call nu U, which has the property that for any Borel subset, either you have this one, nu of E is mu of E if the set E is in the regular part, or infinity if U intersect S of U is not empty. This property comes from the fact that it is an autoregular. You consider it as an autoregular Borel measure. So it is a limit. The value of this set is the limit of the value on open set containing E. Okay. So you have this one, this notion of Borel autoregular Borel measure. You have a critical value. There exists a critical value. Up to now, there is no critical value. Okay, there is no, it's just only Q is 1, Q bigger than 1. Now, the critical value comes from the fact that can you admit what kind of measure you can take? Can you have solution with a strong blow up at one point and 0 outside? And this has been studied by Friedman and Bresis and Peltier and Terman, Bresis, Peltier, Terman in between 82 and 85. Now, if Q is subcritical, then for any K positive or 0, there exists a unique function U equal UK, which satisfied integral of, when T goes to 0, of integral of UK of xt zeta of x is K zeta of 0. So now it becomes infinity C. So it is infinity of 0 or C, depends. We have two notation in France. Okay, so this is just a solution with a Dirac mass. Solution with a Dirac mass. Now you can also let it's a unique, it's positive, and it's an increasing function of K. So the question is what happens when K goes to infinity? So when K goes to infinity, you have there exists a limit, which called U infinity, and U infinity has this very specific form, which is U infinity of xt is T minus 1 over Q minus 1 times W of norm of x divided by square root of T. This was discovered by Bresis, Terman, Peltier. This is due to the fact that in Friedman-Bresis estimate, you have a local estimate for the solution. Well, you have the global, a very simple global estimate that any solution of ut minus Laplacian u plus uq is 0, is bounded by the solution of the differential equation phi prime minus plus phi q is 0, which is plus infinity at 0. This is 1 over q minus 1t times 1 over q minus 1. So this is a universal, but it's not local. And Bresis and Friedman show actually that there is a local estimate that you have solution which may blow up on some set, and it goes to the which are controlled outside of this set. So with this, you can control when you let k goes to infinity here. And this is the result for what you have a localized solution. So this solution, okay, you look at exactly this solution. This is the very singular solution of Brésis, Terman, Peltier. It satisfies this equation here. So this is due to the variable here of this expression. It is positive. Okay, W should be capital W prime is 0 because it's a regular problem. And this is a key point. That means the limit when eta goes to infinity of eta 2 over p minus 1, W of eta is 0. Well, what does it mean? It means that u infinity of xt goes to 0 when t goes to 0 and x is different from 0. This is exactly this expression here. So this is this very singular solution of Brésis, Terman, Peltier. It's unique and it plays a very fundamental role. This is notion of the microscope. Okay, and it's going to be you can estimate with this it plays a role because we know that it blows up over the set over 0. It blows up like a t minus 1 over q minus 1t times 1 over q minus 1. That means the flat solution, but it's very local. But now you can do a little things. Now what happened? You take a solution, a subcritical q between 1 and qc. U a positive solution of this equation in q infinity. You assume that it has a trace. This trace is the singular part here, S of u, which is not empty, times and on the complement this radon measure. So if you look at what happened on a set on a point y in the singular set, then you have that u of x and t is bigger than this u infinity, but concentrated at the point y. That means u infinity of x minus y and t. So the VSS which blows up of y. The very singular solution blows up of y. This is not difficult. This is constructed by using a kind of stability of the stability of the problem. This was proved by Brésis and Friedman. Stability when you make approximation of initial data with measure, and you put below. The idea is essentially that you can put below the function u if it has a strong blow up at the point y, you can put below a function uk for any k. And then you let k goes to infinity. And since you know that the limit of uk is u infinity, you are done. Okay. This is essentially the idea of this. But you see that the maximum principle play is important. So you have this is, I call it phi infinity of t, the solution of the maximal solution of the ODE. This is this one. Now you have, if you take, okay, any solution of the equation ut minus Laplacian of u plus uq, with q is bigger than 1, is smaller than phi infinity of t. This is a maximal solution of this equation. So you have, if u has initial trace s of u, and for example, and 0, you assume that there is no regular part, it is reduced to 0, then you see that the u of xt is bounded from above by phi infinity of t and from below by u infinity of x minus y and t. This is valid for any y in S of u. And the interesting observation is that if you take x equal y, for example, u infinity of at the point y, x equal y, that means u infinity of 0 and t, it blows up at the same rate, not the same constant, of course, but the same rate as phi infinity of t. And in a paraboloid over the point y, you have always the same type of blow up also. This is an important observation for the next draft. Now, you consider a closed set, and I want to construct a maximal solution, you can construct a maximal solution with blow up on and a minimal solution. I will give the details just after. So you construct a maximal solution U upper bar of S and 0, and a minimal solution U lower bar on S is 0 with initial trace S and 0. Okay, you have this one. I will detail how to construct, but you have in subcritical case no real difficulty. Of course, what you have also, of course, the maximal solution is larger than the minimal solution because they have the same trace. But thanks to the estimate that we have before, this estimate here, we have also an estimate on the other side. That means the maximal solution is bounded from k times the minimal solution. And this is a key observation. And from this, we will show that U upper bar of S and 0 and U lower bar of S and 0 they are the same. You will see the proof is very funny, and you will see, I will detail it after. Now, if you take any measure, U on the complement of this set, you take any positive radon measure on the complement of the set, and a positive one, then you can prove that, okay, you can construct by techniques of truncation and so on, a maximal solution with the initial trace S mu and a minimal solution with initial trace, the same initial trace S mu or nu, okay? And what you prove is that by an argument of convexity, you prove that the difference between the maximal solution with mu and the minimal solution with mu, this difference is bounded by the difference of the the maximal solution with 0 and the minimal solution with 0. And when you have this implies that the two solutions coincide. All right, how to solve this mystery? Because it's not completely obvious, but I'm going to give you the details of this. The principle of the proof, essentially we concentrate on the principle of the proof that the U upper bar S0 is U lower bar S0. So how to construct U upper bar S0? What you do, you are thickening the set S. You thicken the set S. Set S is just a closed set, okay? But you thicken it in the sense that you look at S epsilon should be less or equal here, is a set of X in Rn such that the distance from X to S is less or equal to epsilon. So it is a closed set. Now you can construct a solution which has a strong blow-up on S epsilon with infinite value on S epsilon. Essentially, the idea is that only, it should be U is missing here. This solution, actually, it blows up this US epsilon here multiplied by T1 over Q minus 1, blow up at the maximal rate on any open subset of S epsilon, okay? And now when epsilon decrease, US epsilon decrease. So it's increasing, I'm sorry, here it is increasing because of course when you make the S epsilon smaller, then of course the blow-up set is going to be smaller. Since you are constructing by approximation with finite data, there is no problem of comparison. So you have a monotone increasing function. Now how to construct the minimal solution with a set, the same singular set. You consider a countable set AN in subset of S. Now you consider the measure mu n is n times the sum from J to n of delta Ag. So this is a finite sum of Dirac masks. then by Bresis-Friedman, you can prove you have a solution which exists. Okay. Now, and u mu n is, of course, smaller than us epsilon. Now, when n increase, then the u mu n is increasing. So it's bounded from above, and it is increasing, so it admits a limit. The other one, I'm sorry. Okay. So this increased to some us bar 0. So this is a really minimal solution with closed set S, because this must be a small, this one must be exactly larger than any solution with a data, finite measure data, finite direct data in the set S. Of course, it is smaller than this one, and it is smaller than this expression here. So you see that you have constructed the minimal solution with a singular set S and below and zeros, a regular part 0, and the maximal solution. Now, if you assume that those two quantities are different here, those two functions are different, then you have this by the strong maximum principle. Remember that we have an estimate between the maximal and the minimal solution with blow-up set S and 0 here, because of the a priori estimates. So now the maximal solution is bounded by k times the minimal solution. And now you introduce this strange object. Is the minimal solution minus 1 over 2k, the maximal solution minus the minimal solution. So this is positive. So W is less than the minimal solution. But a very straightforward convexity argument shows that this is W is a super solution, and this super solution is smaller than this minimal solution. Also, it's very simple to see that if this is a solution, 1 over 2 plus 1 over 2k times u upper lower bar S0 is a subsolution, because this is smaller than 1. Then, and it is a subsolution, and it is smaller than W. So the consequence, you have a maximal, you have a super solution, you have a subsolution. The super solution is larger than the subsolution. So very standard construction shows that in between, you have a solution. But this initial trace, the initial trace of the solution that you can construct between W and this one, well, it is exactly S0, because both W and this expression here has initial trace S0. So you have constructed a solution with initial trace S0, and it is smaller than the minimal solution. So this is a contradiction. So this assumption is not, that means that this hypothesis is not possible. So this is this funny argument which shows a uniqueness. And now the fact that the solution US, the difference between U upper bar S mu minus U lower bar S mu is less than U upper bar S0 minus U lower bar S0. It's also a convexity argument. So now we're going to explore a little the question of the supercritical case. No, it's okay. I go to the called the Bresis-Friedman removability result. Bresis-Friedman shows the following: when they study this equation, ut minus Laplacian plus uq is 0. They prove that if you have a solution which is continuous in the closure of qt minus the point 0, 0, which vanishes on at t equals 0, except at 0. Then if q is bigger or equal to this critical value 1 plus 2 over n, then the solution is identically 0. If provided, of course, it vanishes on the lateral boundary here. Otherwise, in any case, the solution has no singularity. That means the singularity is removable. So this was the first observation. That means there exists, of course, means the consequence is that there is no very singular solution, because it cannot exist in that case. And actually, the singular, the VSS of Brésil-Sterman-Peltier was only proved, the existent proof, in the case where Q is less than QC. Okay. Second observation, which is also a deep result by Barras and Pierre, actually, they characterize completely a closed set, which are removable. You take F in Rn, you assume that Q is bigger than QC. F in Rn is a compact subset. Then you assume that this capacity, okay, it's a question of Ritz capacity, C 2 over Q prime. This takes the capacity with respect to Rn. And if this capacity is 0, then the solution can be extended as a solution which is continuous in Q bar minus F times 0, can be extended everywhere. I'm sorry, this is not clear what I say. You take a solution in which has initial trace 0 on Rn minus 0, okay, then it can be extended as a solution with initial trace 0, not only on Rn minus F, but also on all Rn. So if you have lateral boundary value in the whole space at infinity, consequence that a solution which is continuous in this term, okay, this is okay, I think it vanishes exactly on the complement, should be the complement here, is identically 0. Okay, this is not very well written, but it is just a removability. That means that the set F is removable. Okay. What is this capacity? This capacity corresponds, it's called the Ritz capacity, or it's very close to the Bessel capacity. It's associated to this, the norm of the Slobodetsky norm of semi-norm. This is the norm of phi q prime to the 2 over q prime is integral over R2n of absolute value of phi of x minus phi of y to the q prime divided by x minus y, so n plus 2 over q minus y. Okay, and this capacity, and usually the capacity is a sharp way to measure set. It's a sharp way to measure set, which is not connected to the standard measure process. Not connected to standard measure process. There are connections, but not with standard measure. Okay. Okay, the consequence is if Q is bigger or equal QC, of course, you cannot, you have no solution with Dirac mass because you have no solution with isolated singularities. But actually, you have also no solution with every radon measure. You cannot take any radon measure on in order to be in order to solve the problem. In order to solve the problem, ut minus delta u plus uq is 0 with the initial value mu. You cannot take any measure in the sense, for example, here the Dirac mass are too concentrated, but it is a question of the measure in some sense must not be too concentrated. Okay. The result is the following. The result in what kind of measure can be admitted for solving the initial value problem with initial data measure. Then you assume that Q is bigger than QC. Then there exists a positive solution of the equation 101, that ut minus delta u plus uq, with initial trace mu in R plus, if and only if you have this, the measure mu is absolutely continuous with respect to the capacity, the Ritz capacity C2 over Q prime. That means C2 over Q prime of F is 0 implies that mu is 0. Mu of F is 0. Okay, this is so it's a very strong restriction, but it really is a question of concentration of measure. It's really the question of concentration of measure if you want to solve the problem. So usually when you have a result for removability of set, you have parallelly a result for you have a parallel result for the for existence of solution with measure. Okay. Now, what are the solutions? You have the set of what are the positive measures which satisfy this estimate. This is a measure which are absolutely continuous with respect to this capacity. I quote them MQ plus a positive measure, MQ plus of Rn or MQ plus of G if I take a set G which is where the measure vanishes outside G. Okay, and if you have a measure in this set, you can construct a solution with initial value mu, and I call it U mu. Okay. Now, what the question is, what kind of set can be constructed? If you have now in the supercritical case, when can we construct a solution with initial trace S mu? You need two things. You know that you need the measure not to be too concentrated. Okay? And you need also S not to have, in some sense, not to have zero capacity. Okay? Okay, but of course, those two things can be combined. Those two things can be combined, and because the singular set of a solution can be created by the fact that the measure blows up here. So the result is the following. You have a solution with initial trace nu is S mu, okay? In the supercritical case, in some sense, two reasons. First question is, mu satisfies 5, 6. Okay, that means this estimate that mu is absolutely continuous with respect to the capacity. So the measure must be absolutely continuous. And now the singular set S must be the union of two sets. The first set is the set of points belonging such that the y in S such that the mu of b epsilon of y intersect with S, C, the complement SC is infinite. That means essentially that the measure blows up on in this sense, it blows up at y. Remember that mu is a radon measure on the complement of S, so it may blow up on the boundary, of course. Not you have this is a first part, the blows up. S should be the union of the point where the measure blows up, and its union also of the set S star. This is a point of Y, such that the local capacity of C2 over Q prime of B epsilon of Y intersect with S is always positive. So that means, in some sense, this is a point which are called intrinsically not removable. And this is so in that sense, this is a condition for solving this problem with S mu. And the solution that we obtain is a maximal solution. It's a maximal solution among all the solutions with initial trace S mu. The question of the minimal solution is a very complicated story. Okay. Now the problem is the following. That's a very funny observation. Actually, it was this first observation was made by a probabilist, Jean-François Le Gall, who was working, he was interested in this equation, ut minus Laplacian of u plus u square in his study on of Brownian snake. It's a probabilist instrument. But I'm going to show you the following. If S is different from 0, there exists no minimal solution with initial trace S. Okay, with initial trace S0. Okay. And this is very surprising. What? Why? Remember that is a solution is Q is supercritical. So you say, what happened when you take a solution? When you look at this, you take a point BR. Okay, if Q is supercritical, then the Ritz capacity of BR, this Ritz capacity of BR goes to 0 when the radius goes to 0. This is due to the fact that the capacity is outer regular. It's an outer measure, actually. And the capacity of a point is 0. Okay? This implies that the limit when R goes to 0 of U of BR, U upper bar, is 0. And this is local uniform. I call U upper bar BR. U upper BR is a maximal solution with initial trace BR 0. Okay, this can be always constructed because this is a ball. Okay. Now you take a dense sequence in Rn. I think it's a dense. Oh, what happened? You see me? Ah.
Oh, only the blue screen.
I have blue screen too. What happened? Aha. Stop code. Critical process died.
Something wrong with your computer.
My computer, okay.
Yes,
With your
your
computer,
computer.
something. Your PC can run into problem and needs to restart.
Okay, I have to restart. Okay, restart. Okay. Because I don't know what happened there. Okay, so you have to wait a little.
Mm-hmm.
You will see just me on the other computer. But I'm astonished because I have the same problem on the two computers.
Mm-hmm.
So, and one problem, one computer is good, but two problems on two computers is too much.
Mm-hmm. Mm-hmm. Oh,
Okay.
now it is.
Ah.
Now it's okay.
It's okay now, but I don't see
Yeah, but now
you,
screen.
I see you. I see you, but
okay, we did not see your screen.
Okay, that's a pity, because this is the most interesting part of me.
What? At least we see you.
Fuck! Oh!
What it means,
What has happened?
Yaroslav?
I don't understand. Okay.
Probably some bad persons. I don't know who it is.
I don't
Some
see my
noise from-
screen again. I don't see where. Okay, I'm going to share my screen.
Mhm.
But no. What's wrong? Because you have two computers, it's too much.
No, your co-host on both computers, it should work.
I don't see. Yeah, I don't see anything now.
In
I
both
try to.
cases, you can send Vika your slides, I should say.
Yeah, it's a pity.
Yes, it's pity, but it's a solution.
Yeah. Well, yeah, it's a big pity. Okay, I don't see what happened.
Mhm.
I guess it was some hacker attack.
There is some perturbation from outside.
Look to this reaction, and this was attack for your computer.
It's not coming from my computer because the same computer shows the same blue screen.
Mhm.
So I think they are not. And if I want to share screen now, I don't see on this one. I no longer see this the desktop.
But okay, but are you still able to send the slides? Okay, now we see your screen.
You see my screen, yes, but you
Yes.
don't see.
Just open your file.
Okay, I'm going to open my file.
Yes, just open your file.
Okay, where is it? I have to see where is my screen. I have to see where it is because, of course, I have too many. I have too many things.
That's usual.
I'm looking for to see where I put it. Trace, no. Trace, yes. Ah, no, this is not the, no, it's not the good one.
Another trace.
Trace is good, but
Another subject.
it's not another, yeah, it's another subject, but I am, it's very strange.
I can remember file was called Rudium2 and it's in upper right side on of your screen.
Ah, yeah, no,
It's
block, because in
just second from the right.
You see, yes, Alexander is correct. Just go on the right. Yes.
Yeah.
A little bit. Yes, and second one from the.
Ah, yes, I see it now.
Yes.
This one.
Yes.
Okay. Do you see?
Yes, and
yes,
please just do this sign. Go, please go down.
Oh yeah, no, I we go. But now the question is, do you see?
Yes,
Yes,
we
yes,
see.
yes, yes,
We
we
see,
see your screen.
just go to
First page. First page.
First page. Yeah, I understand. But now I'm going to try to see if you want full screen. No.
Yes.
Okay.
Nothing happened, I guess.
No,
Now it's
no.
okay. It's okay.
It's wonderful,
Okay, but,
wonderful.
okay, now I have to go to.
Yes, just go to the correct.
Okay, we are. Okay. Okay, I'm going. I continue on this. Okay, now everything is fine.
Yes.
Yeah.
Okay.
Okay. Was okay.
Now, okay, now I'm going to do this one. You consider a set, okay? You take, for example, S maybe, you can even take S is Rn, so no problem of Rn. You take a dense sequence in Rn, okay? For any n, you can find you have a decreasing sequence. You assume that Rn is positive and it decreases to 0. Okay, and I call Un is U overline. This is the solution which blows up exactly on the closed ball Brn of An. Okay, now you have this solution U of the sum of the Un is a sum of solutions. So it's since you have an equation for which the sum of solution is a super solution. So you have this capital U is a super solution. Now U V is the max of the UN. It is a sub-solution. So when you have a solution, a super solution and a sub-solution, you have a solution in between. Okay. Now the fact also that you take the Rn small enough, so the U of X and T can be finite and small enough. You can take, for example, U of X and 1 to be less than epsilon for any U of X and 1 is smaller than epsilon for any xt in this, because you know, because of this property, and you know that the solution the UN goes to 0 when Rn goes to 0 because of the capacity here. Okay. Okay, now you have the minimal solution, the maximal solution, but you see also that the solution capital U and capital V, so these are solutions and they blow up exactly on each point, on each ball Brn of An. Okay, so in between you have a solution which blows up on each ball here of among this Brn of An. Of course, they are becoming very, very small, but they blow up on this the same ball. So if you take now any open set in Rn, this open set will contain a point of a ball BRn of AN. So that means that the solution, since UN blows up exactly on B at the maximal rate on B of AN of R, on BRn AN, that means that any point in Rn is a singular point, but you have a singular point. Okay, that means the singular set is all Rn, but you have the fact that the solution that you construct as a singular set which is all Rn, but the value at u of x and 1 can be is less or equal to epsilon. Okay, so this is proof that you cannot have uniqueness. And in some sense, and this is a very strong observation, and this is this one, that you have a, okay, by standard methods, you have a positive solution which satisfies this, and which has a trace, the same trace of the trace of u is the same as the trace of v and the trace of u, but it is a maximal because any open set contain a ball, and so it is a measure nu infinity, which is the measure which blows up everywhere. Okay, and you take okay, this is what I told you, that u of 0 and 1 can be made arbitrarily small according to the choice of Rn. What does that mean? And this is an observation which is due to Sergei Kuznetsov, was somebody working with Dinkin at the time. It proves that the Euclidean topology is not fine enough to distinguish between the different solutions. Why? Because we use a technique of averaging. Averaging, remember, we define the singular set by averaging of a ball, but averaging with standard open set of Rn. Averaging of standard open set is not, an open set is rough, very rough. It's very rough, so you have to make another notion to introduce a finer notion, a topology which is finer than the usual topology. The good topology is called the fine topology, which is associated to the C2 of a QQ prime capacity. These were ideas, I think people working in harmonic analysis, they use a lot this notion of fine topology in order to see the very fine details of harmonic function. But it works also for nonlinear equation. Okay. And first, now we go into this world of called the supercritical case. Supercritical case is a bit more complicated because I'm going to essentially to explain a little. You have the notion of sigma moderate solution, and sigma moderate solution it's a solution which is an increasing limit of a solution with initial data un. Remember that now Q is bigger or equal to QC. Okay, so the measure un must be measure which are absolutely contained with respect to the C2 of a QQ prime capacity. Okay, a notion. So this is in some sense a solution which are constructible, and the measure. The problem is to construct the solution on a closed set, because if you make a thickening, you will see it's a very rough. Thickening is extremely rough, and you will not see it very sharply. But now you take a closed set, you take the maximal solution, okay, and we can define a notion of maximal solution with initial trace F0. Okay. This is the minimal solution is u upper bar f. The maximal solution is a u upper bar f. And you have this one. I recall this following form, that u lower bar f is the max of the u mu, with mu are admissible measure with compact support in f. Okay. Now the question is, we do the following result. This is the key result. I will not go very far after that, but the result is that the maximal solution with initial trace F0 coincide with the minimal solution with a trace F0. It proves that the maximal solution is also sigma moderate. That means it can be constructed by an increasing sequence of solution with initial data measure with compact support in F. So this upper bar F, in some sense, plays a role of the microscope in the study of the supercritical case. And this microscope, of course, it's a very rough microscope, not compared to the very singular solution of Bresis-Terman-Peltier, which was just concentrated on points. And this one cannot be concentrated on point because they are removable. So there is a notion which is this one, it's called the notion of capacitary potential. Capacitary potential is something which is called it's a nonlinear Wiener test. And it is this one. You take a closed set F, you can define this capacitary potential of F in the same sense. That means I call it WF of X and T. So this is this ugly sum. This ugly sum is 1 over T to the N over 2 times the sum of T to the N plus 1, okay, this power here, time exponential term, this is a damping term, times the capacity of Fn divided by T square root of N plus 1. What is Fn? Fn is just the spherical shell when X minus Y, it's around the point X minus Y is between square root of Tn and square root of Tn plus 1. So this is a very complicated object, but I think Wiener tests also are complicated, so it's not very surprising. And interesting to see that this capacitary potential is not really a solution. It's not a solution, but it has the same scaling invariance as the equation. That means you have this expression, K2 q minus 1 WF of Kx and K square T is the same as W of K minus 1 F of K minus 1 F of X and T. That you, of course, you change the size of F, but you have the same scaling invariance. So it proves that it is a good object. Okay, and the main result is called a quasi-representation formula, which I prove with Moshe, that if Q is equal to QC, there exist two positive constants C1 and C2, depending on F and Q, but not on capital F, on N and Q, but not on F, such that you have the C1 WF is bounded by the minimal solution U lower bar F, the maximal solution U upper bar F is bounded by C2 WF. The proof is utterly technical, 40 pages of computation, which is very complicated. Of course, it's not a problem to discuss, but it is very complicated one. And up to now, I don't think that more than 10% of the world has read it completely, maybe. But not even I'm waiting for a simpler proof, but you know, this is up to now, I have not seen any. Okay, you can also construct like in a Wiener test, you can construct an integral form of this of the capacitary potential. This is an expression. It is nicer, but I think it plays no real role except that it is for the pleasure of eyes. Okay. Now the consequence, an important consequence of this estimate that proves that the U lower bar F is bounded by K times U upper bar F. Now by this argument of convexity we have before, this implies that U lower bar F and U upper bar F coincide. This is the same convexity argument. You construct a super solution which is less than the U lower bar F. Okay, you have this. Okay, this is a little story about what you can characterize a singular set when you have the set when you want to see what happened when under what condition the solution which has blow up set F blows up locally. Okay, and you have this type of thing. So it's now just a word about what is this horrible fine topology. This horrible fine topology, it's horrible because it's not CP. You say that the fine topology is you define notion of scene set. Scene set is a set E, which is called 2 over q prime sin at point A, if this integral of, you see here, you have 1 over q minus 1, is you take the capacity, or this 2 over q prime capacity of E intersect with BR of A, divided by this term, and for the power 1 over q minus 1, the other R is finite. So in some sense, that means that there is not a lot of matter of the points. That means E is very thin in the natural sense. If it is not thin, it is thick, not too complicated. And a set is C2 over q prime open if any point is A in the set E as its complement, which is in its complement is thin. Okay. And with this, I'm just going to show you this, just to say I will not go, but you have a kind of dichotomy also. And with this dichotomy, you can construct, the dichotomy is expressed a little differently. It's because if you cannot integrate directly UQ, you cannot integrate directly UQ on a set G, because G, it is just C2 over q prime open. It may have zero measure. So you take E to the T delta, the exponential here, heat equation with initial data, characteristic function of the set G. Okay. So you have this notion, this dichotomy is this one. And with this one, you can construct a singular. All the technique after that can be constructed in the same way. They can construct a precise trace, and the precise trace, but the importance of the notion of precise trace is that the new measure, you have a measure on the regular parts. The regular part is a union of C2 over q prime open set, and the complement is the complement here is I'm sorry. This is a regular part is a union of C2 over q prime open set, and the singular part is just a complement of this set. Is going to be C2 over q prime closed set, or should be closed here. Should be close. Yeah, neighborhood. Okay, it's okay. So this is you do it in the same way. On the regular part, you have a measure. You have a measure. So the only difference is of this measure now is that it blows up. It is not a radon measure, but because it's going to be continuous with respect to the C2 over q prime topology. That means that the value of this measure on a Borel set is the limit of the value of this measure on C2 over q prime open set containing this Borel set. So this is a different notion of measure, but you can define this measure. It's a measure for which it's called. And now this set, the precise trace and the measure here is called the precise trace of U. Okay, I will not go to C. I just say that the final result that it's a work I've done with with Konstantinos Skikas. We have proved actually that the solution is uniquely determined by its fine trace. Now you have some extension, say you some extension. One extension is a equation. You replace the Laplacian of U by the P Laplacian of U. Okay, it's of course it's a little more complicated, but you have the same principle, and this is done by Veron, Chassain, and myself, and then after that Nguyen and myself. You can also replace the Laplacian by the fractional Laplacian, and this is something I've done with Chen. And okay, you have also some extension of this type of equation here with a gradient term here instead of U to the Q. So the difference is the regular part is easy to obtain. The singular part is much more complicated, but we have some work with Nguyen. And finally, you can also mix the story here. dt u minus Laplacian of u plus a grad uq plus b times u to the r here. Assume that AB is, well, interesting case is AB negative, because when A and B, for example, A and B are both negative, this is going to be a superharmonic function. A superharmonic function has always a positive solution of a super caloric function, has always initial trace, which is a random measure. And A positive, B positive, that means both cases, while the construction is probably more complicated, but I think it's you can construct a outer regular Borel measure, but uniqueness is very far from hope. Okay, so I think I can stop because I think I've been very long.
Dear colleagues, let's thank our speaker for a very interesting lecture. Are there questions?
Oh, I would like to ask something.
Yes, please.
Laurent, what
Yes.
you represent also some generalization, not only heat equation with power-like absorption, but in the different another terms. But
Yes.
What we with you studied was influence on this phenomena of the absorption potential, h of t, which
Well,
and as I see, it is possible to generalize all this question about uniqueness, about initial traces, also for how it depends all this phenomena on such a generation of h of t, because when the critical value changes and so on, maybe it will be very interesting. Maybe somebody studies such equation also.
But remember, even if you want to start with, if h is between two positive constants, no problem.
No, h tends to 0. H tends to 0.
Now, if h either vanishes somewhere or blows up somewhere, this is probably more complicated, because remember that with the starting points, essentially, when you take test function in order to estimate to speak of singular or regular points, you have to absorb a parasite term coming from the integral of grad u g. Remember the beginning, grad phi g square. You have to absorb it by times u. You have to absorb it by integral of uq times phi j. And if you have not integral of uq times phi j, you are going to have integral of h of xt uq phi j, or phi j square, for example. So if you want to use a Hölder inequality, it will be more difficult because you don't have the term h on the grad term. I'm going to, for example, to go back immediately to the initial, to the first.
Simplest case, because without gradient, but minus Laplace plus h of t u to the q.
Yeah, but I told you the equation of how to absorb.
No, that is technique. I speak about phenomena.
In some case, you can do it. Maybe you have to see under what condition. For example, you can have Hölder inequality. Of course, you have a sequence, or you have points. You have a good potential. I don't know, probably Mekenop to weight or things like that. We can work, but. But you cannot take for any potential, because, for example, even you can imagine that your potential is 0 on a your potential vanishes on some open set in Rn. So you are losing completely the control over this set. You just have a heat equation on it.
H of t, not h of tx, but h of t. You see this case.
H of t. Okay, h of t. Okay. Well, h of t. I think it very strongly depends on the. Well, you have to see. First, you have to look at the first at the solution of the ODE, which is very simple. Ut minus
Of course.
plus h of t uq.
No, critical value is very easy to find.
Solution is easy. So it will give you an upper bound, a universal upper bound. Okay. And now you have to, I think, okay. I think that you have, when you have, okay, I have to see.
Yeah, I understand. That's a simple calculation, but
but
it's about phenomena. It will
be
another
okay.
phenomena.
Okay, the question is again how to absorb this. Okay, in that case, if you have h of t, you will have h of t here.
Yeah.
And you want to have this h of t. You want, okay, you can use it as a weight. You can use it as a weight. Okay, you can say the weight function. So you have integral of uq phi alpha h. Okay, that's good.
Yeah.
But you will have here integral of this term times h of t. So it depends probably. You see, this term has to be integrable. So it depends on h of the type of that means your function must be h must be integrable close to 0, for example. You see?
H.
You imagine that you have here a term h.
Yeah, I understand. But no,
But
H,
you use Euler inequality with weight h. So you have h here again and h here. The question is how to handle this term. So if you can handle this term, and you will have it. If you can handle this term, it's okay. And this will be possible if h is integrable close to 0.
No, h tends to 0.
If h tends to 0, there's no
0, of course, it is because of 0.
Well, I told you that I don't make this assumption. I just look at what happened. If h tends to 0, there is no problem. It will be absorbed. You can imagine h. Imagine h here.
But the critical value, it depends on this how it tends to 0 h of t. The critical value of q, because it.
Therefore,
different situation between q more than
Andrei, when you are speaking on the basic trace problem, you don't have critical value respect to q. It's always the existence of the trace, in this sense, is all valid for any q bigger than 1. No question of criticality. If you want to go further, that means to see if you have precise estimate, you need criticality. But when it's just existence of a trace does not depend on q. Okay, but if you want to construct, of course, solution which are below. You need condition. I agree with you. You will need the condition of existence of solution with direct mass.
Yeah, what we started with Konькov started to do, for example, in elliptical case, condition of removability of equation with higher order, even elliptic equations. With absorption which depends on t and u to the q, and we obtain some characterization of this set for necessity condition for removability, which depends on the behavior of h of t.
Yes, no, I agree. I quite agree.
I guess that in parabolic case, when even in this context, but because you told about many very thin delicate properties. But I mean, it is my proposition. But my question, maybe, do you know some activity in this direction? But
no, I don't think. I think the first idea would be to restart completely. To study the question of heat equation with ut minus delta u plus h of t times uq.
Yes.
And first to study the trace, there will be no problem of the trace is h is integrable close to 0. I don't say that it is necessary that it goes to 0, but it must be integrable. So you cannot take 1 over t. H cannot be 1 over t, for example. But you can take 1 over t to the alpha for alpha less than 1. Okay. Now with that, for me, for the initial trace, there is no question of growth. Okay, but now if you want to have, you want to see under what condition you see, can you have this? Okay, this
Yeah.
critical value will be changed.
Yeah, of course. But
Okay, okay. What is the value? The critical. You know, how you know what is the critical value?
We know with you. We know how it depends.
Yeah, I think you just you look at the heat potential. You take the heat potential to the power Q, and you see if it's going to be integrable for the measure h dx dt.
Yeah.
It will give you exactly the condition.
Yeah. Mm-hmm.
But and if it is integrable, so probably you will have solution with k times direct mass. If not, no. And you will have a very singular solution, probably, but of course it has not been done in one sense, and the other is not true. And when there is no singular solution, when you are not happy because you are obliged to develop a heavy theory, as you see.
Yeah. No, clear. Yeah, I would attract your attention because really it generates very many questions for more complicated absorption.
Yeah, no, but no. I think it is interesting to try to.
No, I would like. Maybe we will contact with you.
Yes, of course.
But now I see. Now we understand elliptic case in more,
yeah.
But parabolic case we also try to do.
Okay. No, it's interesting.
Mm-hmm.
It's interesting because Okay.
Are there any other questions?
Well, let me ask a question.
Laurent, may I ask you the following question?
Yes.
You have at the end of your lecture, you have mentioned papers of Di Benedetta.
Yeah, well, yes.
But as I remember, approximately 12 years ago, he considered nonlinear parabolic equations with non-homogeneous boundary conditions in the form of measure.
Yes.
Tell me, please, is it possible to generalize some of your results to this case? I mean, non-homogeneous boundary conditions, which can be written in the form of measure.
Okay, if you can have something that we tried with Moshe. We're interested also to look at boundary. You can look at boundary removability results for the same equation, for equation 914, or even for P equal 2, that means the heat equation. Okay, we have studied this. Now for non-linear boundary, for boundary condition, you can say with non-linear boundary condition, the example is du over dn, for example, plus du over dn plus uq is 0. But you have to see that in that case, it makes things more complicated because for example, take the caloric function, take a dtu minus delta u is 0, and you impose du over dnu plus u to the p is 0 on the boundary. Okay, this is or you can take du over dnu plus u to the q is equal to some measure on the boundary. So this problem which can be handled completely. It can be handled completely. Is it possible or not to have with singular point on the boundary? I'm not sure. It depends what you put inside. If you put inside heat equation with just heat equation, it's not clear. If you take a strong absorption, then you will control some blow up. But this is just my guess. It's just my guess. But the thing has to be done, I think.
Thank you. Thank you. Dear colleagues, are there other questions?
I have a question.
Yes.
Yes, please.
Could you please get back or maybe forward to equation 9.16?
1.16.
I think it is almost the last page, the last slide. Maybe.
What page?
I think maybe one before the last.
What before the okay.
Almost last.
At the end.
Almost. Yes.
Yes, this one.
Yeah.
Yes.
I see. Results in the stationary case boundary trace. I see. Let me write it down.
Yeah.
Perhaps you could tell me.
There are okay. I think there are results.
I shall find it.
There are results by Marie-Françoise Bidot-Véron and Dow, I think, on this type of equation. This study is a trace for this type of equation. Yes, the study completely is a trace, she told me. So the trace is known now for this type. I'm sorry for this, I've forgotten it. The trace is the question of trace is completely known now. It's completely, I think, at least in the subcritical case.
I see. Hopefully, I will find.
Yeah, you can find this is a work of Marie-Françoise and Handau was he was her student.
I see. Thank you.
Okay, and now but you still have this one, and this one is an interesting case. Well, this is, I present this one because it's interesting, because when A and B goes in the same direction, then I think it shouldn't be too difficult to hear. One of them is bigger than the other. I'm not so clear. When A and B goes in opposite direction, for me, the problem is really open. When B is negative and A is positive, that means going to be up to this perturbation is going to be a superharmonic function. It's not B. I have some hope that it can be handled. But when A is negative and B is positive, this is not easy because you have an opposition between the two terms. You have a strong opposition between the two terms, and this is not clear what could happen. Okay,
and what about this? This one is it published?
Well, this one is not known.
Is it completely?
No,
is this completely open?
What is known is the boundary trace of minus Laplacian of U plus A grad UQ plus B to the UR. The boundary trace for the elliptic equation. You can define boundary trace. It's a delicate case between we have the opposition between A and B, and it is a series of work that we have done with Marta Garcia-Huidobro and Marie-Françoise. But for
but in this equation 917, very important relation between Q and R.
Yeah, of course. Yes. But I don't know what is a critical. I don't know what is a critical. In some place it depends. In some case you have the Q is dominant and the R is dominant, and you have a combination. I don't remember what is
very many cases.
But there are many results. In the case of the stationary equation, there are a series of results done with Marta Garcia-Huidobro and Marie-Françoise. I think they are published in CVPDE or Discussion and Continuous Dynamical System. You can see many results on that. Also, there is in Matanal, and I think there is one in Matanal. But this is for the elliptic.
Dear colleagues, are there questions? Another questions?
Laurent, for this equation, if R is very large and Q is very close to 1, what main tendencies? When this equation is familiar to equation with one of these absorption terms, what is such understanding? Qualitatively?
If R is very large, and assume that B is positive. And you assume that B is positive and A is negative, okay?
Yeah.
Okay. In that case, if Q is R is very large, then probably it is clearly that supercritical respect to R, but not. It may not be okay. Take A and B positive. Okay. First, take A and B positive. In that sense, you have to take into account the fact that the result of Marie-Françoise and Andau. Where B is 0. And there is a complete study on that. Now, if B is not 0, is positive but not 0, and R is very large, you have a very delicate problem of intersection with a critical value of notion of critical value. So I don't know what is in that case. I believe that the critical value for R even should be the same as 1 plus 1 plus 1 n plus 2 n, and but for both cases, for the UQ, I don't want to say too much things because I'm not completely sure what could happen here.
Well, thank you.
Colleagues, are there any other questions? If not, let's thank our speaker again.
Thank you very much.
Veron, thank you very much.
Thank you very much.
It was a very impressive lecture.
Thank you.
And there are a lot of very interesting and very deep results, which are very useful for our colleagues because maybe not very fast, but we remove our activity step by step to non-linear paths of transformation.
Sounds good. Sounds good.
Yes, and therefore your lecture is very useful for all of us. Thank you once more very much, and we hope to see you again.
Oh yes, and really and physically.
Physically, I understand that you will take part online, but of course,
yes, but
it
really
will be possible. Physically, we are ready to buy your ticket and to pay for your accommodation, because some of our foreign speakers will come to us personally. It's possible also because COVID